Hello, rising 7th graders. The purpose of this video is to review integer operations. Now that's something that we spent a good deal of time on toward the end of 6th grade. Many of you have mastered it, but like with any topic in mathematics, mastery, even practice beyond the point of mastery so that something becomes so automatic, so natural, that we can free up our minds to deal with more difficult problems in the future. This is something that's extremely important in math. Please take that seriously. Truly mastering a topic, an understanding, or a skill and making it your own. Before we review integer operations, let's talk a little bit about what that is and where we're going to be headed very early in 7th grade. In mathematics, there's a regular pattern to our learning, and it goes something like this. You learn skill A, and then you learn skill B, and you're presented with a problem, a situation where you have to combine those two skills. And in middle school, there may not be a better example of this than when we have to transition from integer operations to rational number operations. And this happens as, right behind my head here, it says, this happens early in 7th grade. Now this video will not concern rational number operations. Early in the 7th grade course, we're going to define what rational numbers are. It's not difficult. For our purposes right now, though, let's think of them this way. Rational numbers are fractions or decimals and their opposites. So negative fractions as well as positive fractions, negative decimals as well as positive decimals. And by the way, the integers themselves are rational numbers. They are special kinds of rational numbers. You should know the integers by now. The integers are the whole numbers, 0, 1, 2, 3, 4, and so on, together with their opposites, and they can be represented here. They go infinitely to the left, all the way to negative infinity, and then eventually, if you're heading from left to right, you'll get to negative 5, and then negative 4, and so on, get to 0, and then continue with the counting numbers, 1, 2, 3, all the way to positive infinity. So those are the integers. By operations, we mean the 4 basic operations of arithmetic: addition, subtraction, multiplication, and division. As you also know now, in middle school, we tend to get away from the X for multiplication and also this symbol for division. You'll see as we proceed here that I will be representing multiplication and division differently than you encountered them in 3rd and 4th grade. So let's get started with a review of integer operations. Early on in our school year, I will present you with instruction, both in class and by video, of rational number operations. Taking any two rational numbers, fractions and negative fractions, decimals and negative decimals, and adding, subtracting, multiplying, and dividing them. So we have to do the same thing with all rational numbers that we first have to do with integers. And is it challenging? Yes, it can be challenging because you have to, at the same time, within seconds of each other, you have to be able to think about the sign, the proper sign that you must end up with in the operation, as well as how do you calculate with fractions? How do you calculate with decimals as you learn throughout 5th and 6th grade? Here's some good news. In terms of the sign, there's really no difference in how you approach the rational number operations, the fractions and decimals and with their negatives, as you do the integers. In terms of how you approach the sign of the answer, there's no difference. So that's something to be hopeful about. And just pay attention, work hard, and it will come. This is something you all can master very soon. So let's get started with some examples of integer operations. So here we have 4 addition problems, and these 4 addition problems really represent anything that can happen except getting a result of 0. But you know how to get a result of 0 when you're adding. Add 2 opposites. So since I kind of forgot that possibility, let me just show you there. -3 and +3 are opposites. If you add 2 opposites, you get 0. And the reason for that, as we're going to explore on this number line with what are known as vectors. Vectors are arrows. The arrows have a certain length and a direction. We're going to represent positive numbers as arrows to the right, negative numbers as arrows to the left. And the way addition works with these vectors is we take the end point of one vector and put it on top of the start point of another. The start point is, the end point is the arrow, and the start point is the other end without the arrow. So here we have the 3 pointing to the right and the -3 pointing to the left. And if we take, either way, addition is commutative. Let me just do it one way. You should understand it works the other way as well. If I take that red vector and sort of lift it up, slide it, so that its beginning point is at the end point of the other one, so there's the red vector representing -3. I've translated or slid it so that its beginning point is at the end point of the other one, and notice where you end up, at 0. They sort of overlap each other perfectly, and so we might say they cancel out to 0. All right? So that's when I said earlier that the 4 I chose represent everything that can happen. That wasn't quite true, because here's another situation. Let me now go through and just give the answers, which I think all of you know, to these 4 addition problems up here. We'll talk about how you do approach them, how you get to the correct answer, sort of mentally, and then we'll look at movement along the number line with the vectors. Now, you're not going to be doing this movement on the number line with the vectors very long, or if ever. This is just to give you a solid understanding of why it works. But the mastery means you've got to look at -5 plus -7, for example, the second one, and know immediately that it's -12. I'll be showing you why with the vectors now, but the mastery of it and being able to get that answer immediately is part of your challenge. 5 plus 7, of course, is 12. And I grouped -5 plus -7 together with 5 plus 7 because you approach them very similarly. In other words, when you're doing -5 plus -7, you're adding 5 and 7. But then make the result -12 rather than +12. When the signs are the same when you're adding, your mental process is addition. But when you're adding the 2 negatives, it then becomes -12 instead of 12. We'll see this with the vectors. Now, the other 2 are completely different because the signs are different. And when you are adding 2 numbers with different signs, the mental process that you're doing is subtraction. Now, they're still additions. It's 2 numbers with a plus sign between them. But the mental process you go through is subtraction. And the way I usually say this is, you take the absolute values of each number. We've talked about absolute value. We'll review it. But the absolute value of -5 up there is 5. How far is it from the number line? How far is negative 5 from 0. That's what absolute value is, the distance of a number from 0. The absolute value of negative 5 is 5. The absolute value of 7 is 7. So you do 7 minus 5, just like a first grader does, and you get 2. And for that first one, the answer is in fact 2. Why? Because the positive 7 is further away from 0 than the negative 5. The 7 has a greater absolute value than the negative 5, so the answer ends up being positive. The vectors will show this. For the final one up there, you're still going to do 7 minus 5 because the signs are different. You have a positive number added to a negative number. But this time, after doing 7 minus 5, you have to realize that the answer is negative 2. Because this time, the negative 7 is further away from 0 than the 5, so you have to go with the sign of that one that's further away from 0. So there are the 4 answers, and now let's quickly look at the 4 additions in terms of vectors on the number line. So for 5 plus 7, we see the 2 vectors pointing right, representing 5 and 7, both of them pointing right. From 0 to 5 for the 5, and from 0 to 7 for the 7. We place one of the vectors so that its beginning point is at the end point of the other one, the end point being the arrow and the beginning point is the non-arrow end. And it doesn't matter which order you do this in. This is a great way to see the commutative property of addition. But let me take the 5 vector, and instead of having it start at 0, let's have it start at 7. This may remind you of first grade where you might have learned to count on. How do you do 5 plus 7? Or 7 plus 5 in this case. I guess I've done it as 7 plus 5. Of course, it doesn't matter. You go to 7 and count on by 5. And of course, you're going to end up at 12. So there is the 5 vector being placed starting point on end point, and of course you get to 12. And this is addition of 2 positive numbers, which you already know how to do. The addition of the 2 negative numbers is going to work in a similar way, except you're going to go to the left. So for negative 5 plus negative 7, or the other way around, we have the 2 arrows, vectors both pointing to the left, and we move one over, and you can see that, hopefully you can see here why you add 5 and 7, but then make the answer negative, of course, because the arrows are both going the same direction. They're both negative. So I took the 5 vector and repositioned it so that its start point was at the end point of the negative 7. And of course, the 2 combined extend all the way to negative 12. I think you can just see that there. So that's half of addition. Now let's look at the other half. This is now negative 5 plus 7. Notice the arrows go in opposite directions. Positive 7 is a vector that has its beginning point at 0 and its end point at positive 7. And negative 5 begins at 0 and has its end point at negative 5. But we're going to move one of them the way we've done before, except this time the 2 lengths are not going to combine to become a greater length. The length is going to get smaller, and this goes along with subtraction. Why? When the signs are different, your mental process is a subtraction. So what I did just there is reposition the -5 to here, endpoint and beginning point, and notice that -5 does not reach 0. It reaches, of course, to 2. And if you're wondering, is this -5 plus 7, is it the same as 7 minus 5? It is. But that'll have to wait till subtraction. When we define subtraction, you'll know that to be true. Let's look at the final one now. This time, we still have 2 arrows going in a different direction, but this time, of course, -7 and +5. And again, please understand and play with this on paper if you need to, or at least look at this number line and convince yourself that it doesn't matter which vector I move and reposition. We'll get the same answer, and that's the commutative property of addition. Let me pick I will pick the -7 to move. And this time, by moving that -7 vector so that its beginning point was at the end point of the 5, it actually now extends beyond 0 all the way to -2. So there we have addition. I'm not going to use the number line for subtraction because we're going to define subtraction to be a kind of addition. We're going to define subtraction this way: to subtract a number, add its opposite. And hopefully you understand the addition with the vectors on the number line, so we can just do it all abstractly without reference to the number line when we do some subtractions. Please notice what I did here. I took each of the additions above and replaced that addition sign with a subtraction sign. So instead of 5 plus 7, we have 5 minus 7. And instead of -5 plus -7, we have -5 minus -7. Instead of -5 plus 7, we have -5 minus 7. And instead of 5 plus -7, we have 5 minus -7. So make sure you see that. And actually, I hope this isn't too confusing. I thought it was just sort of logical to replace each plus sign with a minus sign. But over here on the left, when we were adding and we had 12 and -12, that's not going to happen down here. The two kinds of additions are actually going to sort of switch positions somewhat. But how do we subtract a number? We subtract a number by adding its opposite. So 5 minus 7 is 5 plus the opposite of 7, which is -7. So 5 minus 7 is 5 plus -7. So this one here is actually over there as an addition, -2. See, it's the same addition as this one. Okay? Down here we have -5 minus -7. So we see this as a subtraction sign. How do you subtract a number? You add its opposite. We have to add the opposite of -7, which is 7. So this one becomes -5 plus 7, which is 2. So when I replace the plus sign on each of those additions up there with a subtraction sign, we actually got the 2 over there. Now we move to negative 5 minus 7. Well, how do you subtract 7? You add negative 7. To subtract 7, you add negative 7. Negative 5 plus negative 7. And that, of course, that becomes this one, which is negative 12. Here, we're subtracting negative 7. How do you subtract negative 7? You add the opposite of negative 7. You add 7. So this becomes 5. The 5 minus negative 7 actually becomes the simple 5 plus 7. That was the first addition. Now, one way, a really good way that I want you to commit to memory, get very used to, is this definition of subtraction as to subtract a number, you add its opposite. And notice when we're doing that, the first number doesn't change. You know, we're subtracting a number. The number on the right is being subtracted. We add its opposite, leaving the first number alone. And it's kind of like keep, change, flip for division of fractions. You leave that first one alone. You change the division to a multiplication, then you flip the second. It's a similar sort of approach to subtraction, which is to subtract a number, you add its opposite. But there's another way to think of subtraction, which might help some of you. You use whichever approach, whichever understanding works for you, whichever verbalization causes you to have that deep understanding. You be the judge of that. But I want to present you with another way to look at subtraction by saying that any subtraction is really a question about addition. So let me erase a little bit and present the same ones that way. Let's sort of back up a little bit to first grade. A first grade teacher could very well present to his or her students subtraction in the way I'm about to. Maybe you can recall this approach. To say that a subtraction is really a question about addition. So the first grader sees 5 minus 2 and might think, what do I add to 2 to get 5? That's subtraction, a question about addition. What do I add to this number to get the first number? Well, right here we've got 5 minus 7. The first grader, of course, does not get that problem. We've already talked about seeing this as 5 plus negative 7. I'm not changing that, but you can also look at it this way. What do you add to 7 to get 5? Now that's a nonsensical question to a first grader. First grader would think the teacher made a mistake. What do you mean? You can't add something to 7 to get 5. First graders only understand positive numbers, whole numbers which are positive. But we know there's a number you can add to 7 to get 5, and it's negative 2. How about this one? Now this is the subtraction, right? And then this second number is negative 7. What do you add to negative 7 to get negative 5? And that's 2. Think about it. I'll say it again. What do you add? This is a subtraction, so it's a question about addition, and the question is this. What number do you add to negative 7 to get negative 5? And the answer is positive 2. The same answer we got before. And again, I'm not saying you have to remember it both ways. Maybe you will. You'll remember the way that works for you. And the best way to really learn it is through practice. And if you get some wrong, sometimes you do 20 of them and you maybe get 2 wrong and they kind of look the same because you got a little bit of an issue with one type of problem, and then you fix that and you move on. So there'll be a lot of practice as we've had before, and you'll master these. Over here, we're subtracting 7. So we have to ask, what do I add to 7 to get negative 5? What do I add to 7 to get negative 5? And that's negative 12, isn't it? And finally, here's the subtraction. The second number is negative 7. So what do I add to negative 7 to get 5? And the answer is 12. If you want to now rewind a little bit, go back a little bit, and see that with the definition of subtraction as the addition of an opposite, we got the same results. So again, you use the approach that is best for you. Now, I see that it's 26 plus minutes here, and we need to cover multiplication and division. But earlier this summer, you watched a video about multiplication and division, and the real purpose of that, or the purpose that was most important to me and I hope to you, was to understand why the rules work the way they do for multiplication and division. And I say all the time to 6th and 7th graders, multiplication and division with numbers with various signs is easier than addition and subtraction because the rule is so simple to state and apply. And if you recall from that earlier video, and also during 6th grade, we've already covered this, if you're multiplying or dividing 2 numbers and the signs are the same, the answer is positive. In other words, 2 positives multiply to a positive. 2 positives divide to a positive. 2 negatives also multiply to a positive and divide to a positive. So if you're multiplying and dividing 2 numbers, if the signs are the same, the answer is positive. And of course, if the signs are different, the answer is negative. So a negative times a positive is negative. A negative divided by a positive, or a positive divided by a negative. Either way, if the signs are different for multiplication and division, the answer is negative. So I might have said earlier that we're going to do all 4 operations, but seeing the time, and I have a tendency to go on sometimes, and because I really want to explain the math so that you believe in it. That this is the purpose. You might think, well, we could have covered this in 10 minutes instead of 30, and yes, but if that deep understanding and that belief in what you're doing is there, then you're much more likely to have success in the future. So again, for the multiplication and division, refer back to that first video from earlier this summer. I hope this has been both enjoyable and educational. And as I sit here today, we're more than halfway through August 16. We'll be together soon. I look forward to it, and I hope you do too. So long for now.